Transformations of logarithmic functions. We're going to work with a problem in our notes, and there's going to be a couple pieces I'm going to want you to adjust just because of the way the graph was formatted on this page. We're going to make a couple adjustments, so just kind of hang with me as we work through this. But what we're going to do is we're going to take this function m of x equals the log base 3 of x plus 2 plus 5, and we're going to go ahead and graph that. And one of the things I want you to remember is, just up here we have various exponential. By the way, the other day we did 2 to the x, we did e to the x, we did 3 to the x in our prior class. And obviously their associated graphs, their inverses are going to look like the log base 2 of x, the log base e of x, in other words, ln of x, and the log base 3 of x. So we've actually kind of built some of these pieces, some of these inverses already. But today, what we're going to focus on is transforming a logarithmic function. So first things first, hopefully we already know from what we learned today that a logarithmic function is going to have a shape like this with a vertical asymptote at x equals 0 and behavior kind of driving straight down, and on the other side is going to continue to increase and go off towards infinity. But we're going to have this type of shape curve. That's point number one to notice. Now, for what we're going to do, you're going to be asked to graph log base 3 of x plus 2 plus 5. And our parent function is going to become the log base 3 of x, so one of these types of shapes. And we're going to talk through that as we build in a few moments. And then we're going to be asked to treat this as a parent and identify the transformations of log base 3 of x plus 2 plus 5. And in looking at this, plus 2 inside the logarithm function, that's a horizontal shift left by 2. Plus 5 outside of the logarithm, outside of the function, that's going to be a vertical shift up 5. So that's what we're going to wind up having to draw. But first we're going to have to build our parent. And we'll talk about that process in a couple seconds. To begin with, however, here's what I'd like you to do. I've already made the adjustment. Let me just give you a different copy of the notes page for a moment, just so you can compare and contrast. What happened on the notes was the bottom of our graph got truncated just a little bit. I'd like to have had a little bit more in-depth down here. So here's the correction that I'm going to want you to make. Number one, just go over here and put the word range, because that was missing down at the bottom as well. We're going to identify the domain and range of this transform function in a few moments. But also what I'd like you to do is what looked like the original x-axis. What I'd like you to do is do exactly what I've done here. And what I did is I just took the x-axis and moved it up. The x-axis, equation y equals 0, so to speak, is going to live 2 units up. So just make note, don't treat this bottom black line as your x-axis. Instead, treat it as the red line. And then what I've done in purple, I've built log base 3 of x, the parent function. And if we recall from some of the things we did before, I recommended that you do what? That you be real comfortable with some basic table structures. In other words, know some key points of y equals 3 to the x, and I've highlighted some of them. -2, 1/9, -1, 1/3, 0, 1, 1/3, 2, 9. And we know that log base 3 of x is the inverse of y equals 3 to the x. So to get the points that I would use on my parent function for this problem, y equals log base 3 of x, all I have to do is flip-flop this table. And that's what you'll see here. Give me a second just to refold my paper. That's a little bit better. And there are some of my key points for y equals log base 3 of x. 1/9, -2, 1/3, -1, 1, 0, 3, 1, 9, 2. And I've gone ahead and put these points out here. These are my parent function, some of my critical anchor points. They're going to be the ones that I'll shift. There's 1, 0, 3, 1, and 9, 2, which I had to extend out just a little bit. Now, I also have, and I can't just see it right here, but we also had our good old vertical asymptote at x equals 0. So now all I need to do is take these points. I'm going to work with each of these anchor points, and I'm going to do exactly what I talked about. Shift left 2 and up 5. So my 1, 0, when I shift left 2, that's going to become -1 and then go up 5. -1, 0 now becomes -1, 5. -1, 1, 2, 3, 4, 5. There's a point. I'm going to do this in green. Okay, 3, 1, Move over left 2, 1, 2. Move up 5, 1, 2, 3, 4, 5. There's my next point, which happens to be at 3, 1. Now becomes 1, 6. And finally, 9, 2 is going to become 7, 7. Over 2, up 5. So 7, 7. Let's find it. 1, 2, 3, 4, 5, 6, 7. 1, 2, 1, 2, 3, 4, 5, 6, 7. And then what else do I know? Well, I could take my other points, but what do we remember? My vertical asymptote lives now at x equals negative 2. Here it comes. And what do? Just repeat the purple curve. Now make it the green version. And here we go. Right on down that vertical asymptote. Just fill it in a little bit harder. And there is my transform graph, what you see in green. 3 anchor points. I've now moved them to new green anchor points. And bottom line, let's go ahead and work out our last piece. Just go to a pen that's working a little bit better. My range, it didn't change. Oops, excuse me. Negative infinity, positive infinity, all real numbers. My domain, well, look at that. Everything, the function doesn't start until what? Until you're to the right of the vertical asymptote at x equals negative 2. You never touch negative 2. Your domain is negative 2 to infinity. So this is a very brief walkthrough of transformations of logarithmic functions. What's important? Well, hopefully you're going to start to understand how to build a logarithmic function using some of the nice little characteristics that we talked up here. You have an x-intercept, so you know 1, 0 is always a very, very nice anchor point, just like we saw with our original parent. Because we're talking about log base b of x here with all these different characteristics. You also remember that what? b comma 1 is always a point on your logarithmic function y equals log base b of x as well. And in our example, that was certainly true. So those are the basic pieces that I want you to work through. Be comfortable with these transformations, and we will go from there.